The following program is brought to you by Element 14, the electronics community where you can connect and collaborate with top engineers from around the world. Join now at element14.com/presents.
Hi and welcome back. I thought today we'd just do a fantastic little painting, and I think you're going to enjoy it. So I'll tell you what, let's start out and have them run all the colors across the screen that you need to paint along with us. We'll start with our standard pre-stretched canvas, and the first thing you want to do is load some paint on your old 2-inch brush. Today we're going to paint a happy little robot, so just pick a spot where you want to start and just brush it down like that. There. Just like that, little crisscross strokes. And just enjoy it. You know, looking at this gives me an idea. Why don't you join me at my workbench right now, and I'll show you what I mean. I'll see you over there.
Amazing hacks. Inspired designs. Each week, Element 14 Presents brings you innovative projects using electronics, engineering, and more.
Hello and welcome back to Element 14 Presents. I'm Andy West, and as you may have guessed from the intro, in today's episode we're going to try and build a robot that can make art. In fact, many of us already have machines at work or home that can reproduce artwork, and we call those printers. But I want to build something more interesting to watch. A device that could put pen to paper and draw an image line by line. Something like a robotic arm, maybe? Now, I've never designed a robot before, and I've also never built one, so what we're going to do is start with this basic kit and modify it with additional hardware, and then we'll program it with our custom software and make it do our bidding. Looking at this, you can see that it's very simple. This is actually an educational toy that's been around for several years, and they're quite inexpensive, which makes it an ideal starting point for our build. Over here on the virtual whiteboard, we've got our robot, and you'll notice that it's manually controlled, which we don't want. So we'll get rid of the control box and replace it with the Raspberry Pi and a motor controller board. I chose the Pi so we can make this all self-contained, which will make coding and debugging a lot more seamless. Another thing is that these motors don't provide any feedback, so we need to add a sensing mechanism to each motor in order to get accurate, reproducible movement. Okay, let's look at what we've got in this box. Alright, this is pretty nice. Everything seems to be here. I've decided to mod this as we build it, rather than do the whole thing and then have to partially disassemble it again. Luckily for us, this gearbox assembly is the first thing in the instructions, so this is a great opportunity for us to figure out our motor feedback solution. Now, there are many possible ways to do this. One way is to add potentiometers to each joint. The downside is this could be fairly bulky and obtrusive and might even restrict movement. Another option I considered was to add infrared LEDs to the arm and then use motion capture or machine vision software, but that seemed a little too complicated. I finally settled on using something called an optical encoder. They're simple, they're cheap, and I'm pretty sure I can fit the whole thing right inside this gearbox. To demonstrate how optical encoders work, I'm going to tear down this old mouse. Now, this is a pre-USB era optomechanical or ball mouse. There's literally a rubber-coated steel ball underneath here that rolls around when you move the mouse across the surface. Alright, let's open this up and take a look inside. Okay, so you can see how when the ball rolls, it turns these two little wheels on different axes. And if you look closely, there's all these little slots. On one side of each wheel is an infrared emitter, and on the other side is a detector. And these slots either block the infrared beam or let it pass through, depending on the position of the wheel. So if we hook this up to the oscilloscope, and give it some power, and then move the wheels around, check it out. The sensors we're going to use are all one piece. The emitter and phototransistor are packaged together, and the slot in the middle is where the beam crosses. I figure we can test these out on a breadboard with a little Python on the Raspberry Pi. We've got a 10K pull-down resistor on the detector side, and using Ohm's law along with a spec sheet, we find that we need at least 34 ohms on the LED side. The closest thing I have is 47 ohms, so that's what we use. This little snippet of Python code should be enough to test if it's working. And look at that! When we break the beam, we get a change in value. Perfect! In the mouse we inspected earlier, we saw a slotted wheel positioned in the beam. For our gearbox, we've also got wheels in the form of all these gears. The motor itself has a screw-like gear called a worm, and that meshes with the worm wheel, also known as the worm gear. We want to mount the optical sensor, so the worm gear is positioned in the slot, because that's the fastest turning gear and will give us the highest sensing resolution. Rather than try to cut tiny slots in the gear, we're going to drill several holes, and if you look at just the right angle, you can see small circular indentations that'll serve us perfectly for positioning those holes. This is a small part, and we don't want to just start hacking away with a rotary tool, so I got this small drill that fits in the palm of your hand. We'll start with the smallest bit and gradually move up until the holes are the size we want. You want to take your time with this because we've only got one shot. This kit doesn't come with any spare gears. Wow, that came out really clean. I think this is going to work great. Alright, now if we assemble these gears the way they're going to fit together in the gearbox, you can see that the gap there is just exactly big enough to fit the sensor. We definitely don't want those touching and creating friction, so I'm going to try to carefully cut one of these open with some flush cutters. That worked okay, but you can see how these components are loose without the packaging to hold them together. I'm going to put a small dot of super glue on each of these to hold them in place. Now we've got plenty of clearance between the gears, but before we go any further, I want to test the sensor again. Oh man, it's not working. Okay, we're going to have to fix that. So it turns out the packaging we removed was doing a lot to block ambient room lighting. So to fix it, I gradually increased the resistance to dim the LED more and more until it worked. A resistor value of 2 kilo ohms seemed to do the trick. Going back to the gearbox, we want to cut away enough material to make room for the sensor, but there's one problem. We need to mount the sensor consistently and accurately on 4 separate motors. So to help, I'm going to make a 3D printed mount. A little bit of glue in the right spot, and we'll have a perfectly positioned sensor. I found some flat 4-wire cable to solder in here, and it's a little bit bulky, but it looks like it just barely fits when you close it up. Look at that. The cable fits perfectly through that slot, almost like it was by design. We'll be using a Raspberry Pi to control our robotic arm. This is the Pi 3 Model B Plus starter kit, which I got from Element 14, and I really like these kits because they come with everything you need, including an appropriate power supply and an SD card with noobs pre-installed. You should never wire a motor directly to the Pi unless you want to release the magic smoke. What we need is a motor controller board, and I found one that can handle our 4 DC motors. It has lots of cool built-in features like PWM-based speed control, and it also conveniently uses a Python library, so we can have our sensor code and our motor controller code all in one script. The controller exposes the Pi's GPIO pins on top of the board, so we can wire up the sensors there. And I've put together a script that runs the motor at half speed and prints the sensor value when it runs. This is great. So what we've accomplished here is the ability to control motors from the Pi, and also detect how much they've moved, and as an extension of that, their position, which is very important if we want to be able to draw something. Alright, I'm going to finish building this, and when I come back, we'll figure out how to coordinate the movement of all these motors, and hopefully program it to do something useful. Now it's time for some community feedback. In a recent post, Justice Johnson wrote, "Just out of curiosity, has anyone else here tried actually putting this together? I did, and it didn't work right out of the box for me. When I looked through the logic analyzer, it seemed like the bits were being read from the receive line consistently a few hundred clock cycles too early. So I changed the debounce hold off to 800 clock cycles, so now it tries to read bits exactly in the middle between 2 bit boundaries instead, and voila, it worked. I was just curious if anyone else had the same issue that I did or not." It's always great to hear from viewers who decide to try these builds on their own. And Justice, you're absolutely right. Precision timing is essential when dealing with communication protocols like MIDI. And ideally you want to be able to test with as many devices as possible. Of course, when doing a build for a video, time is a limiting factor. So great job in finding this issue, and especially for sharing your solution with the community. And if you have questions or comments that you'd like to share, you can do so at element14.com/presents. As you can see, the arm's now finished, wired up, and ready to go. I'm running the controller board off a desktop power supply since the maximum current draw of the motors is fairly high. There's one part of this kit that we didn't use at all, and that's the original control box. But it still would be nice during testing if we had a way to control the arm directly without typing code. So I'm going to take this old Xbox 360 controller and write a script that'll give us wireless manual control. One additional benefit is that we have analog thumbsticks and triggers, so we can tie those directly to the speed of our motors. In the code, we've got a motor class that lets us configure each motor and track its state. And we've got 4 instances called wrist, elbow, shoulder, and base. We define a dead zone to prevent spontaneous unwanted movement. After everything is set up, we loop continuously, processing input and updating motor state until the back button's pressed on the controller. Let's try it out. This is cool. We can't pick anything up because there's nowhere to wire the gripper, but in theory you could if you stacked another controller on there. Before we can program the arm to draw a picture, we have to calibrate it. In other words, we need to tell the arm what position it's in and what its range of movement is. So I wrote another script, building on the previous script, that lets us reset all the sensor values after we move it to the home position. Then we can move the arm through its full range of motion and press A to print the current sensor values at certain points. I decided to define this position as the home position, and we'll just move this fully up and down, and left and right like so, until we've got all the values we need. Now comes the hard part. We need to figure out how to convert a point on a piece of paper into a combination of rotational positions for each motor on the robotic arm. So for example, a point at XY coordinates -5, 5 translates to a specific combination of motor positions that we have to calculate. This is a common problem in robotics and is normally solved with something called inverse kinematics, or IK for short. Unfortunately, IK solvers can be really hard to write, and all the libraries I tried were either too complicated, slow, or didn't have the features I needed. It turns out that we've got few enough joints, and our motion is constrained enough that we can use basic high school level trigonometry to solve our problem. Looking top down, calculating the base rotation is pretty simple. Python has a function called atan2 that does all the hard work. Working out the other three motor positions is trickier. This diagram shows a simplified view of the robotic arm. Sides B and C of the triangle are constant because the arm length is constant, but side A varies because it represents the distance from the base to the desired point. This can be solved with a distance formula. Once we know the length of our three sides, we can calculate all the angles using the law of cosines. Okay, here we go. We'll test this on a couple of points, and if it works, we'll have the basis for drawing any image we want. It's moving. Nice. I don't want to get ahead of myself. Let's try a different point. Perfect. Now before we try to draw an actual picture, something occurred to me. We can't just interpolate the motor positions to draw between points. To understand why, imagine you're trying to connect 2 points to draw a horizontal line across the page. The base of the robot is going to rotate, but it's going to move the pen in an arc rather than a straight line, and that's a problem. So I think what we want to do is still interpolate the values, but also to draw everything in very short line segments. That way the distortion is local and hopefully minimized. For our first test, we'll write out the words "Hello World." These colored pixels are our 2D points, and the colors are there just to help me keep track since I'm entering this all manually. For simplicity, I'm just hard-coding these values directly. I'm almost afraid to see what happens. It is doing something. That is, well, that's unfortunate. I think I might know what went wrong. So if you notice, when I rotate the base and then change direction, the motor runs for a brief moment before the arm actually moves. This is due to gear backlash, and it's something I can compensate for. As always, I've written a tool to help me, and what we're trying to figure out is the maximum amount of motor movement I can do without moving the arm. That'll be my compensation value. Okay, so you can see that 15 is too much because it's moving a little bit there. It's almost imperceptible, but it is, twitching a little bit back and forth. 10 seems to be the sweet spot. Let's try it again. Well, it's a little better, but it's still not very good. One thing I'm seeing as I watch this is that despite having a good grip, the pen is wiggling a lot forward and back, and that's problematic. So I'm going to try printing a pen holder and see if that helps. So the way I've designed this, the pen can move slightly up and down, but not in any other direction. The idea is that if the arm moves slightly upward, the pen won't come off the paper. Gravity will just pull it down, in theory. That's an improvement for sure. I'm sure that with further iteration it could be improved a lot, but for the purposes of this video, I have to stop here. That's all we have for today. What would you do to increase the accuracy of the robot? Let us know on the Element 14 community at element14.com/presents, and we'll see you next time.